the sort of one major textbook that is always used and cited. That's this one, Greeley and Iverson. It dates back to sort of the late 70s and the Viking Mars landers. So it's dated. And that hasn't really been a problem until maybe 15 years ago, when a lot of information started coming out about sand transport on Mars, and orbital and lander information started to get better, and a lot of laboratory techniques started to come in. So especially over the past few years, many aspects of especially sand transport are really dated now in this book. It almost isn't really worth reading it. If you want to be up to date, you have to read a lot of papers. So until a new textbook comes out, it's what we still have, but it's not really. That's so what we do in my lab, just as a very brief, I'll come to sort of a proper introduction to my lab later, but basically what we try to do is we try to recreate planetary atmospheres in our lab. So specifically kind of low pressure, low temperature environments. So it kind of should be valid for the outer part of every planetary body. But specifically, we tend to look at terrestrial type bodies. So something with a hard surface and a fairly thick atmosphere. And then the obvious thing that happens is there's an interaction between the two and you get particle transport. So this is a very fundamental sort of interaction, a fundamental process that happens almost certainly on all of these bodies. So this is Titan, a moon of Saturn. It has a thick atmosphere, so that's weird. And it is weird. We don't do much about it other than we do study ice transport. So a little bit we do on that. And Mars and Earth you'll hear about. Venus, we don't know much about the surface, so that's a problem. So this is a picture of northeastern Africa. About 1 billion tons of dust leaves northern Africa every year and goes around the world. 200 million tons lands on South America. An estimate of the total global mineral dust transport is about 3 billion tons a year on Earth. And interestingly, an estimate of the total global dust transport on Mars is also about 1 billion tons a year. So even though the pressure is like 100 times less, it's sort of a comparable relative amount of dust transport. So that's a weird thing already without knowing anything about this subject. So yeah, one problem with the textbook I just told you about is that back then, up till about 15 years ago or so, it was not known that sand was transported at all on Mars. So this is a picture of Mars. There's lots of sand dunes and ripples and whatnot on the surface of Mars. The vast majority of them are ancient. They're old. Some of them are millions of years old. The stuff that does actually get transported around are these dark dunes, and they're almost certainly dark because they've shed the dust layer which is on the surface of them. So they look the original volcanic type basaltic stuff that they are. So yeah, this is a sand transport on Mars. It's a relatively new subject in the nobody knew it happened like 20 years ago. So yeah, I'm not really going to tell you much about Titan, other than that there's some really nice pictures of dunes on Titan, which is these. So obviously the environment is very different. It's super cold. It's like minus 200. And these are ice particles that act like sand. So yeah, Titan's interesting. You're not going to hear about it, but so yeah, we also do work terrestrially with a lot of volcanologists. So we were once in a volcanology network, and we interact with volcanologists And a lot of the same science is true of that than sort of normal mineral transport. It's actually the most dangerous thing about a volcano, not the actual eruption, but resuspension of ash which has been deposited. And so a lot of the experiments we do for sand and dust for Mars, for example, are the same kind of experiments we do for volcanic transport on Earth. And interestingly, the upper atmosphere of Earth, the stratosphere, looks like kind of Martian atmosphere, about the same pressure and temperature. Plus, the surface of Mars is actually a kind of a volcanic environment. Hasn't been changed that much, which I'll maybe get to later. So yes, the interesting thing for Mars that we know now is that there's small sporadic transport of sand and there's a lot of transport of dust, and that's what we want to try to understand. So Gerhard showed you a picture that looks a little bit like this. It's so I'm going to go through the terminology. So yeah, dust by definition can be suspended and taken high up in the atmosphere. And that's basically the definition of dust. It's a vague definition, which I'll come to in a minute, and a little bit problematic. It's not really a geological definition. They would call it silt or something. But the process of taking stuff up is different to the process which keeps stuff suspended. So it can be that you can take particles up, but they're too heavy to be suspended. They fall down again. That's basically the definition of sand. So what sand tends to do is it tends to hop. It gets entrained, taken up from the surface, and then falls down again. And that's what saltation essentially is. Then there's particles which can't be taken up, and they can be mobilized by sand grains hitting it, which is kind of called creep, or they can slide and roll around. So yeah, there are these three fractions: dust, sand, and stuff that sort of moves around, rolling. And on Earth, the defining parameter about saltating grains is they don't normally hop very high. The saltation layer, where there's intense transport of sand, is normally only about 1 or 2 centimeters on Earth. And that means there's a kind of an erosion layer, which is only a few centimeters high. And that explains how you get things like this happening in the desert. What happened here is that this centimeter layer of sand essentially has eroded a disk out of this. And then because the surface, for some reason, has deflated, it's eroded a whole section out. And now the surface is down here because it's deflated for some reason. But yeah, this looks weird, and it's saltating grains that do this. And through abrasion simply. And I'll come a bit back to abrasion later on. So this is kind of wind dynamics 101. What happens when you blow wind over a surface? You generate a boundary layer, which is stress coming from the free wind speed up here to the surface, where there's zero wind speed at the surface. And conventionally, normally, you will then divide that into 2 regions. One close to the surface, where there's viscous transport of shear stress to the surface. So you get a viscous layer. And then above that, there's a logarithmic layer, which is where turbulence is the process which transfers stress. And this turbulent layer, so on Earth, this viscous layer is very small. It's only a few millimeters. And normally is not really even visible. It's hard even to make measurements of it. Often the surface roughness on Earth is bigger than this viscous layer, so you don't really see it. The turbulent layer can be valid all the way from close to the surface, a centimeter, all the way up to a few hundred meters. So this logarithmic layer is really what is dominating on Earth and also on a large scale on Mars. But what is pretty cool on Mars is that this viscous layer is quite thick, centimeters thick. So this is a kind of qualitative difference between Earth and Mars in that there's a thick viscous layer on Mars, and this almost certainly affects the transport of particles, how they behave. I'm going to say a little bit about computational fluid dynamics. This is a relatively new technique, and one naively might think, okay, you're basically computing the flow of everything. Surely that you just need to plug everything into a computer, and then then you don't need me anymore. You can just solve everything perfectly. This is not true. We tried. Uh, we tried a long time ago. So this is a model of an actual thing that we built. This thing here, which actually ended up being sent to Mars. And this is the wind tunnel. The wind comes this way. So what you do in a computational CFD model is you split it up into a matrix of whatever pixels you could call them. And the important thing in that process is that in some areas, nothing much happens. So you need really poor resolution. And some areas like this little guy down here, you need an insanely number of actual elements. Otherwise, you don't get the flow going correctly here, and then nothing downwind makes any sense because you've made a mistake, like right there. So this is already becoming problematic that you need information to put into the model already to start with. Then what you do is you basically computationally solve the Navier-Stokes equations, which are basically conservation of energy, momentum, mass, and with a bit of kinematics thrown in. So it's basically, just a set of equations that you can solve. But the important thing is that they can't be solved without you putting in some boundary conditions. And it's these boundary conditions that makes it problematic to run this. So we did succeed in making this model, but what was vitally important was that we could actually do the experiment in the lab and take information from that and put it into the model. And it anyway took a whole PhD. It took 3 years to do this. So it's not something you do over a weekend, even though there's this was a commercial software. So CFD is not the answer to everything, but it is super useful. Then you can put particles into the flow, and then you can calculate drag on them and see where they go, and then you can see if that's correct. So it is a really good technique, but it's not something an easy fix. So that brings me to drag. So drag on particles as well as drag on surfaces is not a trivial subject. It's somewhat more complicated in the sense that as you change scale and pressure, you go through different drag regimes. So for big things like footballs and people jumping out of aircraft, you're in this regime, Newton flow, so it's basically turbulent. Turbulent drag is the dominating thing. But then, so this plot is Reynolds number. So one thing that is characteristic of aerodynamics is that they love dimensionless parameters, and there's a whole analytical system for using dimensionless parameters. What they're supposed to be good for is condensing physics down to a simple scaling law so that everything plots onto one simple plot. And it often works. The problem can be for a planetologist is that often things are based on terrestrial studies, and then you can't just stupidly apply it to another planet because you're varying a fundamental parameter that is not really taken account of. Anyway, if you don't remember anything else from my talk, then you should remember the Reynolds number. If you're having a conversation with a aerodynamics person, this will make you seem really intelligent straight away. Gives you infinite credit. So it is the sort of dimensionless parameter that makes that people know of. People will have heard of it. And what it tells you is essentially the ratio between turbulent drag and viscous drag. So it tells you the sort of transition between where turbulence is the dominant drag factor and the viscous one. So you go from this regime to this regime. And the super weird thing about this viscous regime, often called Stokes flow, is that it's independent of pressure or density. So that's super weird. It means you change the density, but the drag is the same at the same speed. It's very not intuitive, counterintuitive. And the unfortunate thing is that sand transport on both Mars and Earth are pretty much in this transition regime between the two. But if you had to choose one, you would probably say they're in the Stokes flow regime, so the viscous regime. And this is something I'll mention later on. It's kind of important. So when particles get even smaller, then this viscous drag process is also not valid. When the particles get so small that they can see the difference, the space between different molecules, then you get what's called a slip, in that they kind of pass through the holes between the molecules. So yeah, that's when you go into this molecular drag regime. The equation is down here. This is that guy Epstein I mentioned yesterday. He made a really good equation which works very well down in the molecular regime, where your drag is essentially single molecular impacts doing the drag. And it's characterized by when this Knudsen number becomes around 1 or bigger than 1. It is the scattering length or mean free path divided by the particle radius. And this is the regime which is dominant on Mars for like Martian type dust. As I remember, the scattering length on the surface of Mars is around 7 microns, and the particle radius is whatever, 1.5, 2 microns. So you're in the molecular drag regime. There is a sort of equation which is supposed to work between the Stokes flow, the viscous flow, and this. It's supposed to be a universal equation. I hate it intensely because it's got three empirical parameters in it, and there are at least 20, 30 different numbers that you could plug in here. So I'm not a big fan. Gerhard likes it, I can see, but yeah, it's good because you just plug it in and it's plug and go kind of thing. But yeah, I don't know. Yeah. Anyway, so drag is not. So yeah, dust transport is also a little bit problematic because some dust can be in this viscous regime and some can be in the molecular regime. It's problematic that you're in between, and it's problematic for sand as well. This is a visualization of the way I understand it in my head, that every particle has actually all of these 3 drag regimes going on at the same time. So you very close to the surface, it's single molecules hitting, so you have molecular drag in this really close to the surface. Further away, you have a viscous boundary layer, which is dominated by essentially a viscous fluid. And then further away, you get these turbulent eddies, which transport so all 3 things are going on at once. There's just one of them that is dominant, depending on how big your stuff is. So yeah, I'm going to define dust in a slightly more quantitative way. I have used the Stokes drag here, so you should replace that with the other molecular drag if your dust is too small. But kind of the reason why I've used the viscous one here is that this can also be true of sand. So on Earth, high wind speeds can easily suspend sand. So then the sand is sort of acting like dust. So the condition in which you define whether something's suspended is that the turbulence in the flow is comparable to the terminal wind speed of the particle, which is when you're falling so fast that the drag is equal to the gravity. That's the definition of the terminal wind speed. So when these two things become comparable, means that even when you're falling at top speed, the wind can still be taking you up and down and all over the place. So this is basically the definition of when something is suspended. And yeah, the kind of the weird thing is, for example, in a tornado, a house can be under suspension in that the wind can be so insanely big that this actually becomes true for a car or something. So yeah, and they're not dust, obviously, but so the definition of dust is a bit weird, I think. So yeah, that's a condition for suspension, which is separate from the condition needed to take a particle off a surface. This is normally called the detachment threshold or entrainment threshold, which means taking it off the surface, not just moving it. Or some people call it the saltation threshold, which is actually a whole other thing. But common to all of these is that you use a force balance equation to simply balance the forces generated by wind with gravity and adhesive or cohesive forces. So you have, adhesive, cohesive forces, gravity keeping it down, and then the wind normally has two effects. One is a vertical kind of lift force, shear stress, and another one is that it can make drag, which can cause them to roll around. So yeah, when you balance these, you get something that looks like this. So for detachment studies, this is kind of the major article everybody cites. It's actually the same work as Greeley and Iverson book. They've just moved it around a bit so it looks a bit sexier. But it's characterized by really there's two regimes where this is going on here. One is really big stuff is obviously dominated by gravity, and essentially you can assume it's cohesionless. So this is big sand. It's dominated. So it's dominated by gravity. So bigger particles get more and more difficult to move by wind. But the same is true of very small particles. Small particles are dominated by adhesion, cohesion forces, and so they also are really difficult to move. So there's a kind of optimal minimum size, and that basically is the definition of where sand is. The sand is down here. It's the easiest thing to move in principle by wind, normally, is what you say. It may, in fact, not quite be true, but so the problem with this is, or the problem was at least 20 years ago, is that I've shown you several slides and you know this. There's lots of dust transport on Mars, very little, or they thought no sand transport. So how can that be? Dust is down here. It should be really sticky. And already back in the late 70s, early 80s, they realized that maybe it's got something to do with dust sticking together and making aggregates. And so, this is at least 15, 20 years old, this slide. And so this was what most people really thought, that aggregates are involved somehow in dust transport on Mars, but and maybe it works in some kind of cyclic way that the aggregates get broken up. They're detached, then broken up, and under the breakup process, they get electrified, and then they maybe make aggregates again already while they're in suspension in the atmosphere, and then they get deposited again as aggregates. So there's maybe a cyclic thing going on. That was the idea. It's Not really, at least not until now, been definitively demonstrated, at least in the lab. And yeah, not even observationally really on Mars, I would say. But everybody kind of thinks that this is true. Everybody wants it to be true. It solves a lot of problems. Yeah. I will say at this point that already 20 years ago, there wasn't a lot of people studying the surface of Mars think there is a fundamental problem with the wind shear, wind speeds, that they're too low to transport sand. That was never entirely true. They were definitely on the wrong side. The wind speeds were really too low, so it was a problem. But now it's way less of a problem. The wind speeds, if you calculate the wind shear on the surface of Mars during even a local dust storm, or sandstorm, it is enough to transport sand. We're so close, at any rate, it's within uncertainties. So this is to kind of demonstrate that there is a kind of change over the past, whatever, 10, 20 years in the way people are modeling saltation, so sand transport. The conventional view is that you use this dimensionless analysis, analytical analysis, and the model is based on a kind of a cool idea that as you blow wind on a sand bed, you can start to entrain sand grains, and the sand grains, they get accelerated by the wind, but they also slow down the wind flow. So there's a kind of what's called a feedback. So the sand is slowing the wind down, and the wind is accelerating the particles. And what happens when you blow more and more wind over the surface is not that you increase the wind speed down here at the surface. The wind speed, the wind shear stays at the threshold. What you do is you just entrain more and more sand. So as you blow harder and harder on it, start transporting more and more sand, and the sand slows the wind down more. So you kind of conserve that you're always at the threshold at the surface. This is the kind of model that conventionally that's always taught. There's what happens during saltation. With modern techniques like CFD or other models using numerical solutions, you don't need to sort of make this assumption. And there are definitely problems with having this rather simple model of saltation. It kind of is not working, especially for Mars. So yeah, threshold is one thing. What about the transport rate? So one thing that is very obvious is that there's a fundamental difference between a sand bed where the grains are mobile and you get saltation happening. That looks completely different to a sand bed which is essentially not mobile, and you maybe just have a few sand grains. Those two situations are very different. Um, the transport rate in the case where it's immobile goes as the cube of the velocity. And this is what they thought was true also of mobile sand beds in the old days, but it's been shown not to be the case. So if you have what's called a hard bed, a hard floor essentially, and a few sand grains on it, they basically can get really fast and bounce really high, and then you get this kind of transport rate as a function uh, of friction speed. Um, so I probably forgot to define friction speed. This is not related really to the actual free wind speed. So this parameter U star is actually related to the force it's a kind of fake wind speed related to the force on the surface, the stress on the surface. And it usually is a factor of 10 or 100 lower than the actual wind speed because it's some kind of fake parameter. Yeah. Anyway, the point is that so this is shown in this. This is a yeah, non-erodible bed, a hard bed, and this is the erodible one. So they have a very different function as you increase U star or shear stress. The way you prepare your surface. Yeah. So basically, what I do is you get the same particles, you just glue them onto the. So then they're not moving, unless they take the epoxy off. So, yeah. So this is a movie. This is not the best movie to show saltation, really. This is actually volcanic material, and it was taken with our high-speed camera in our wind tunnel, which is not the best. But I suppose it's about 1,000 frames per second, something like that. So it's yeah, they're moving really fast. And this is not a lot of transport here. This is sort of an okay amount of transport. When there's really a lot of transport, it's just totally chaotic. So I'm showing you this partly to show you that, yeah, as Gerhard showed you, high-speed movies are cool and very useful. Actually, you could easily imagine that you can do particle tracking on this and get loads of information, which you then could compare to a CFD model or something. So yeah, there's loads of information potentially in this kind of thing. But I'm also showing it to you because maybe when you see ripples forming on a surface, they're very ordered. But when you actually look at this kind of thing, you think, whoa, it's really chaotic. They're bouncing all over the place. I promised Gerhard I wouldn't mention splash, but I'm gonna have to say it, the actual word, I think. So you can see that they're hopping around, and when they hit the surface, they can knock other sand grains up. Yeah, and some of the cool trajectories, you can see some of them get knocked out backwards and then get hit by the wind and then start going that way. I don't know whether you can see it in any of them. And it's really quite clear that there's a strong gradient in wind speed. The wind speed down here is not very high, but up here it's really fast. So if they get up here, then they get caught by the wind and so yeah, there's a lot going on. There. And so it's then actually, and yeah, so how do you model this? This is actually a new model. So parts of it are conventional, old-fashioned. So there's this feedback layer. So this model is what the group in Paris are sort of fighting for right now. There were other groups fighting for other models. But yeah, I'm mentioning this because they came to our lab and did some measurements to test this model, which is kind of a new model. So they claim that there's actually three layers to this saltation process. There's the feedback layer where you've basically got this interaction between the wind flow and the sand grains that are talking together. So there's kind of a lot of the kinetic energy transport is actually in the form of sand grains in this layer. But then if some of them get out of this layer, then you have this free wind layer where they're just taken by the wind and do something completely else. But they claim there's a layer even below this where there's kind of agitation and collisional things going on, kind of like a fluidized bed type situation. Who knows? That's as much as I understand about the model, to be honest. Yeah, what they're basically trying to understand is a very simplified type of saltation where all the grains look alike. You've got active saltation. How do we model that? That's really what they're trying to then they're not trying to complicate it with broad distributions of different types of particles. They're looking at an idealized sand grain and an idealized flow and try to say, okay, let's try to understand that. And they actually apply this to this dimensional analysis. So they use what's called a Shields number. Anyway, I won't bore you with it, but but yeah, it's very idealized, this model. And they came to our lab to try to test it, and we performed what still are, this is only a few years ago. This was back in 2020-ish. These are by far the best measurements of saltation threshold at different low pressures, um, way better than any other. These are down to percent inaccuracies, whereas before that, they were not better than a factor of 2. And and this black line is what they predicted. So it was working really well at the higher pressures. Then something weird happened at around 60 millibar. And below that, so Mars is down here at around 1,000 kilopascals. So something super weird happens at low pressure that they do not understand. I do not understand it. Nobody understands it. But it's super cool from an experimentalist point of view. It's clearly some kind of new regime of whatever going on down there that is not in their model. No, we do not want more numbers. There's like 100 and something of them already. But yeah, this actually helps a little bit with arguments. Why is sand transported on Mars? In that you get a bit more than a factor of 2 reduction in the threshold needed for saltation on Mars. So it's good news generally for the community. It sort of contributes to solving a bit of a issue. But yeah, it kind of argues against their model. Uh, yeah. So what you're seeing here is a horizontal laser sheet, um, very slightly above the sand bed, which is down here. So not entirely better. Never mind. It doesn't matter. I'll go to the next slide pretty soon. I was just showing this technique because it's actually a pretty cool technique, even though it's really simple. It just uses a laser sheet horizontal across close to the bed, and then a webcam from the side or a microscope. And so it's not a high-speed camera, so you just see like traces of them integrated. So you can't track any particles using this, but what you can do is identify single grains and then by simple intensity analysis, you can actually look at the concentration of sand transport until it gets too much, and then it'll saturate. But this is actually a really powerful, super good technique that is, yeah, it's still new, but it works really well. Oh, that's even worse. It's like dentist noise. So this is a webcam that's looking down on top of a sand bed, which is already generating ripples. The wind is going that way, and yeah, if you, it should start again. Yeah, if you go back and forward, then it'll probably. Yeah, so the wind is going that way, and you can see the ripples are very slowly moving this way, and this is speeded up by like 16 times, I think. So when it's happening, you can only just maybe think that you see that the ripples are moving, but it's too slow really to see. But here you can certainly see that the ripples are moving. And so even though like the particles in themselves, it all looks chaotic, they produce these really nice structures, the ripples, and they're actually moving with a certain velocity, and they have a certain wavelength. And yeah, yes. Yes, before. Yeah. We start always with a very flat bed, and they generate it themselves. Yeah. Yes, yeah, more or less. The wavelength does change as they evolve a little bit. They tend to get longer. They start shorter and get longer, but it's very small. Uh, and as I'll say in a minute, the cool thing is they look exactly the same on Mars and Earth, which is weird given that the conditions are very different. And this is kind of a whole thing that was something that came out of their model, that the velocity and the wavelength of these ripples, they predicted that they would be insensitive to like particle size and also gas density, and that appears to be true and is kind of weird. So this is actually a microscope from the side looking at the sand bed. You can't really see it very well on this. You could probably see it on that one. So maybe you can see maybe you can see that it's forming. So this that almost filling the whole screen is one ripple. So that is about 2 centimeters or whatever between that peak and that peak. You can see it starts flat and then they start to appear, and then they're moving that way. Uh, and you can see they start a bit shorter and then later on they get a little bit longer. And this is all very normal. And on that microscope picture, you can actually see the individual grains. So you can kind of see how the ripple is actually formed. It takes particles from the backside of the ripple and then takes them up a little way and deposits somewhere in the front. And that's how they actually move. And you can see it's kind of a chaotic process. You can see it's a bit jittery and it's not really, but yeah, it kind of, I like that movie because it kind of shows how something that seems to be like random actually generates these structures. I think it's totally the same. Yes. Mm. Yeah. In fact, their model is one they developed for from flumes from water. They claim it's entirely analogous, same process. They even made a dimensionless analysis so that everything fell down on the same plot. Yeah, for water and gas, it's the same. They claim, and yeah, I think it kind of works. So yeah, I've told you a bit about old and new technology for modeling. The same thing is really going on for experimental stuff. So in the old days, we used to use particle traps, basically a little bucket where you'd catch particles and then weigh them. We still use it, but it's crude and it's inaccurate. Yeah, there's lots of really good optoelectronic and laser systems now, which can, yeah, basically identify whole arrays of particle trajectories, velocities in time. So these are particle image velocimetry, which often is where you have a sheet and you basically determine the velocity of every particle going through it at the same time through this area. We have one of these, a laser Doppler velocimeter, that measures in a very small area, but it measures the absolute particle velocity in 2 dimensions or three sometimes. High-speed cameras and lasers, as you know. So, yeah, modern wind tunnel experiments are using these and not so much using these guys. Uh, yeah, this hasn't really started to affect field work. In field work, they tend to use meteorology stations, field wind tunnels. Yeah, so there's a bit of a delay for this to really start impacting, but I can't see any reason why you can't take a lot of these optoelectronic systems into the field, and I think it will happen in the near future. What the benefit of doing it in the field, obviously, is that the turbulent structure of a real wind is completely different to what you do in a wind tunnel. So this is looking at particles being transported by wind from a real sensor in the field, and you can see it's really bursty and super turbulent. And this is kind of hard to recreate this kind of thing in the lab. You need to do field work to really get it. I'm going to tell you a little bit about abrasion. So I told you that sand grains hitting stuff, they can break. This doesn't really happen at really low velocities. Certainly happens at around 10 meters per second, which is kind of a ordinary kind of wind speed. So there you get fracturing, and you can basically disintegrate a sand grain into smaller things, big chunks. What interestingly happens at around 1 meter per second impact velocity is you don't get big fractures, you get tiny little chips coming out, and you actually generate, as we saw, submicron particles, a lot of them. So you generate, very teeny tiny little dust grains out of impacts when they're at low velocity. This may be kind of relevant to Mars. What is definitely relevant to Mars is that I don't know whether many of you ever thought about why Mars is red, but in principle Mars should be gray since it's made of volcanic basaltic stuff, which is gray. But there's a group in Copenhagen that has sent magnets to Mars on basically every NASA mission. And the point of them is to capture the dust, which is slightly magnetic. So they did experiments where they captured this dust. They captured enough to actually do analysis on it. They did mineralogy analysis, and they proved that it's made of exactly the same stuff as the sand. So undoubtedly, the dust on Mars is generated from abrasion, probably due to saltation of the sand. The reason it's red is that it contains an oxidized form of iron oxide. So there's magnetite in the original material, which is black, very black. And then if you oxidize it a bit more, you get hematite, which is really, really red. Even like 1% of hematite mixed in with something really dominates the color. It becomes very bright red, and that's what's happening on Mars. Yeah. So that's a bit of a side issue, but what is maybe not so irrelevant is that it's not just a change in color, it's that the surface has actually become oxidized and oxidizing. So saltation probably directly leads to chemical activation of the surface. And this has also been shown from other studies that the surface of Mars is actually oxidizing. And it can explain why there's almost no organics at the surface of Mars. They get oxidized as soon as they sort of land. Anyway, so this is our lab. What we did was we built a very big vacuum chamber and put a wind tunnel in it. We got originally funded by ESA because they wanted to test stuff before they send it to Mars. And so this is the basic structure. There's a fan section here with two fans. They suck the air down a channel in the middle, and then they return it above and below, and then it meets again in this end. And during the roadmap experiments, we split this. It's about 10 meters long in all, but there's really only 8 meters of useful space. So in this upper section, we made a wind tunnel where we could transport sand and dust. And then we had a downwind section where we could analyze this dust which is suspended. So what tends to happen if you suspend dust here, it fills the whole wind tunnel pretty fast. But yeah, this is our sort of detective sensor system. We can obviously pump it down and make a Martian atmosphere. We can also control temperature, which we didn't do in these studies. And this section is actually a narrower part. So we have a higher wind speed than down here. we can get so high wind speed that we can easily transport sand and, yeah, not all dust. I'll come to that. So this is looking at this downwind section where we have our detectors. I just wanted to show you. This sensor is what I call an opacity sensor. I just shoot a laser sheet through the wind tunnel from the outside and then have a detector on the outside on the other side and measure, how much light gets through. Very simple. This is the laser Doppler velocimeter. So this opacity sensor is like measures the average over the whole wind tunnel, basically. So it's good for that. Whereas the laser Doppler velocimeter only measures in this tiny, tiny spot where they cross. So about a cubic millimeter there is the detector volume, and any particle going in there, we detect it, even if it's submicron. Yeah, and I'm blowing dust in, otherwise you wouldn't see the beams. So this is the setup we used for the roadmap experiments. So I think this was dust on a glued bed. I'm not sure. But anyway, it could also be a soft sand bed. We did both. We made a soft sand bed and put dust on it. And we also had a glued one and put dust on it. And then turned the wind up and saw what happened. One of the referees for one of our papers criticized us because they said that Mars doesn't look anything like a wind tunnel. I disagree. I think this looks almost exactly like our wind tunnel. In fact, it's almost the same dimensions, and clearly it's got sand in, which are making ripples. So yeah, that's pretty cool, I thought. Anyway, yeah. So I'll show you a movie in a second if it works. But immediately, the most interesting thing we saw about direct dust resuspension, so dust just deposited on an immobile bed, is that if it was thin, then we simply couldn't remove it. It's not possible. We went up to the highest wind speeds we couldn't move anything. If you want to move dust directly, it has to be a thick layer, like a really thick layer, at least more than a monolayer thick, which corresponds to many grams per square meter. But then when you get these really thick layers, you can remove it at wind speeds already comparable or even slightly less than the speeds needed to move sand. So this is already pretty exciting. This is really the first time this has been seen. So we could remove the dust and we could see it being removed by the color essentially, and we could detect the stuff that gets resuspended. This is a movie showing how it gets removed. So you can see it's kind of weird. You generate these big aggregates which kind of peel off a little bit like wallpaper. They roll themselves up like carpet, and they roll all the way down. What you can't really see on this movie is that on a smaller scale, there are some smaller particles being removed that don't roll. They just get taken by the wind. Oh, didn't play again. Oh, never mind. Well, anyway, yeah. So you have these two kinds of things. Does anybody want to see it again? Shall I do it? Oh, yeah, of course. Yeah. Stupid me. Yes, of course I can. Yeah, so you can see they sort of peel off from the front and then go down, and then we're increasing wind speed while we're doing this. So this is sort of a higher wind speed. So they're doing something a little bit different here. I think they're basically breaking up. They're being taken off, but they're breaking up. And they do break up, and you can see streaks down here. Some of them get trapped. Yeah, anyway. So yeah, there are big aggregates that roll. There are smaller ones which seem almost to be very similar size to each other, that get sort of taken straight up. So these are very distinctly different, these two types of aggregate removal. And then there's breakup and redeposition. And some of this stuff then gets resuspended, but only a small fraction, actually. Yeah. So that's what happens with dust on a direct resuspension of dust on a solid bed. What happens when you have a sand bed So we made a soft sand bed full of loose grains and with dust on it. And we were hoping that it would start to saltate, the stuff would be removed and get resuspended. Nothing like that happened at all. What happened is that the sand went crazy and started going up at really high heights and going into our fan section and all the way around. It was chaos. So we thought, oh, something weird is going on there. So we decided to study it, even though it wasn't on our list of things we were supposed to do. But anyway, so what we did was we studied saltation and trapped the particles at different heights using these very old. These are actually from the 70s. These traps. So yes, we went old school on it. So we trapped particles at different heights and tried to look at how high do these sand grains go when we've got saltation as a function of different pressures. And then I managed to convince a student to do some modeling of this. It wasn't CFD, but it was something a little bit comparable. He at least took individual grains from the surface and then saw what they did as they went up. And the points are our measurements and the lines are his model. So the model absolutely reproduced what was going on and what clearly is going on. So yeah, I don't know whether you can see. So this is the high pressure. Almost everything is really close to the surface. We only managed to collect a very few grains at 10 centimeters sort of height. But yeah, at the low pressures, like huge amounts are right up to the top of the wind tunnel. They were hitting the top of the wind tunnel. Yeah, and they're basically suspended. That was our conclusion. That, as I mentioned, sand actually in this regime, you're kind of in the viscous drag regime, the Stokes regime, and that is independent of gas density, which is, so it means exactly the same thing happens once they sort of get high. Then their drag is very similar at the high and low pressure. It's almost no difference. So this is a wind speed effect. So it's not related to shear stress, which would be dependent on the gas density. It's related to the fact that, yeah, the sand grains actually, once they've left the surface, they become suspended, which I don't think anybody really consciously thought about. It may have come out of some modeling, but they hadn't actually formulated it in their head that this is actually what's happening. This is good and bad. It's good that it's interesting, but it ruined our experiment because these grains were then getting high up and getting to high velocity, and they were generating huge amounts of dust by abrasion, by hitting everything, hitting the fan, hitting the walls. 125 microns, so close to what is normal for Martian transportable sand. So yeah, this is the amount of dust we were producing as a function of this U star parameter, essentially a function of wind speed. I once had a theory that the abrasion rate should go as wind speed to the fourth power. That's obviously completely wrong. It looks almost linear. So I don't know why that is. That was a very bad mistake. So yeah, but the actual quantity of this stuff is several orders of magnitude more than the other dust resuspension we were looking at. That was like milligrams, and then this is grams of resuspension. Yeah. So this is, yeah, both exciting and kind of a little bit confusing. So yeah, this is basically a summary of, so where do we go from here? We've seen a lot of these effects now for the first time. It would now ideally be interesting to study some of these things more quantitatively, see what they depend on. I'll say one thing is that so we run our lab as a facility, which means we have a lot of visiting research groups, normally funded by EU money, or sometimes by national funds that they get. They normally come and they do some experiment in our wind tunnel, and we love this kind of thing. It's very fruitful. Um, and we have several groups that come and study saltation. So we have at least 3 groups which come regularly and study saltation in not always focusing on the low pressure, but kind of normally always using the fact that we can close it and we don't generate dust in the lab. And nearly every time they come, they see something new that we hadn't expected. So right now there are 3 different observations which have not been published, which all show a counter to the conventional model of saltation transport. So there's really a lot going on right now, which I suspect hopefully will settle down in a few years. And that's the point when maybe a textbook should be written summarizing all this stuff. But yeah, it's saltation is clearly a lot more complex, and by trying to study it on Mars, you really emphasize some of these the new physical processes going on. Dust suspension, there aren't that many groups studying dust resuspension. We will try probably to continue if we can get any money for it. But I don't know whether we can. I'm not allowed to just do experiments in my lab. I have to pay for it. So that's a problem. And I would really like to relate transport rate to abrasion rate because it has this link to surface activation and chemistry on Mars. But yeah, I don't really know how I'm going to do this. It requires modifying my wind tunnel in a way so that I avoid it hitting the fan. So yeah, it requires redesigning a wind tunnel of some sort in order to do these kind of experiments where you isolate abrasion. The modeling, we don't really get involved too much in the modeling. We do occasionally do a little bit like that student project, which was a Monte Carlo simulation, if that means anything to you guys. But numerical simulations are at any rate, they're fantastic for this kind of physics. And there definitely will be more of this going on. But yeah, some of it is unnecessary. I know that on medium scale on Mars, they employ a stochastic approach to dust resuspension. They don't really even use a threshold or use any of our physical models. They just have a statistical attitude to it, and it seems they can make a predictive model that way. So yeah, like I say, the theorists related to sand transport, they really need to go away and have a think right now, because their models are not working. They're not predicting things that we're seeing quite easily in the lab. Like I say, I can cite 3 or 4 different effects now that they have not predicted and went away being very surprised. So yeah. Thanks. That was
Okay, so I like to see the far future. So I ask you a question about the far future. If you had the possibility to send an instrument on Mars to study saltation and resuspension, what kind of instrument would you send?
probably if I had to build one, I would try to link it with a probably I would want to send a laser sheet combined with a webcam or a microscope, a digital imaging thing that could get close to the surface and do what you saw in that side view where I had a laser sheet. And if you did it maybe in the right way, where you had it on an arm, you could maybe have the laser sheet could be orientated different ways. That would be excellent. That would recreate a lot of the sort of micro systems that we use. And it could be low power and quite lightweight. It would just need a laser sheet and a camera that looks like a lot of the sort of cameras they've already been sending.
And the follow-up question is, because there's a lot of talks about the purpose of human on Mars, and they're trying to find reasons for sending humans and things that human can do better. So, are these kind of experiments done better if a human was there doing it, or can it just be done by a robot?
I would say probably yes. It could be quickly done by a human person. But it's not impossible to do it with a robot. It just would be way more complicated and take longer. But yeah, if you sent a geologist there with a laser sheet and a stuff, yes, they could learn an awful lot, probably in a very short period of time. But I guess that's generally true of these kinds of things. But I absolutely think that, yeah, a small dedicated sensor, yeah, that could get really low to the surface. Yeah, that would be super useful. But also there are not really enough wind sensor measurements. So often when you send a wind sensor, previously the wind sensors sent to Mars are usually up here, and we don't want that. We want several measuring the boundary layer. That would be super useful.
Then the problem is how to deploy them, because they are, if they are next to the
Yeah.
GFD working.
Yeah, a technology we've been using a lot now are using pitot tubes, which are very, very simple. They just require measuring pressure differentials. You could have loads of those. Yeah, they're very lightweight, very low power, easy to build. Or you could send something more advanced like a sonic anemometer. These can work in different dimensions, and that can also tell you about the boundary layer. I know there is an American group. They're coming here actually soon to my lab. They're developing a sonic anemometer for Mars. He's not. He's in California. Isn't he in Pasadena? Yeah, he's Caltech, I think. But whether he's Don Banfield, I don't know whether anybody knows him. Yeah, well, he's coming. He spent many years developing this sonic anemometer. But he moved. He used to be in Cornell. Anyway, yes.
Just at the end, you showed some measurements of the dust flux as a function of the friction velocity. And at the beginning, you showed two equations to model this. Did you make any comparison with the equation?
Oh, you mean the saltation induced or the direct dust resuspension?
I mean, at the beginning, you showed also these measurements, but at the beginning, you show also two equations for rigid particles and mono.
No.
Did you make any comparison with this?
This doesn't agree with either of them.
Does that mean we shouldn't use?
It means we don't really know what's going on with this abrasion thing. It is a very surprising that it looks almost linear. Yeah. I can think of no reason why it should be that. It should be like u squared, u cubed, u to the fourth is what I thought it would be. Why it's linear, I have no idea, to be honest. Sorry. If I knew, I'd tell you.
Oh, it's nice. You have some very interesting counterintuitive results. The best. Anyway, a quick question. So you mentioned in your tunnel you use just current Earth atmosphere basically, but you could switch to other gases.
Yeah. So some of these measurements, these were done with CO2 at Martian pressure.
Okay, because I was about to ask, do you expect any difference, or maybe you did already? Does the change in atmosphere actually change anything? Kind of.
We've never seen any difference between CO2 and air, the composition. Actually, I thought that could explain I had a theory that it could explain, where is it? These guys, that I thought gas composition could. So I measured it in helium and CO2 and air. There was no difference. It just, or if you get the fluid density right, then it's there's no composition dependence at all. So that was disappointing for me. That was my only idea. So
Same time, that's one less parameter to.
yeah,
Or
yeah, yeah.
Any gas is good
Yeah,
enough.
the data was very, very convincing. They were completely on top of each other when you scale from, yeah.
Someone mentioned yesterday about the temperature, and you can't really do the cold temperatures because
We absolutely could do this at low temperature. It's just tricky. It's just, yeah, tedious. No, because it's already like 0 down here. It's very, very low. As soon as we pump the air out, it's the absolute partial.
grains contain any.
No, but we do see that they outgas water. So it's normally best to just leave them overnight at low pressure so they outgas this water. Yeah, they outgas probably 2-3 millibars of water, and then we pump it out, and then we do the experiment. But no, we've done some tests looking at the effects of humidity. It needs to be really quite high, absolute amount, before you see any stickiness.
I guess the one thing you cannot modify in your experiments is the gravity. And can you estimate somewhat, maybe from experiments?
The nice thing about gravity is that generally in their model, gravity normally does what you expect it to do, at least for saltation. So their model clearly takes account of gravity, and it seems to do nothing unexpected. There are kind of at least 2 ways where you can kind of fake gravity measurements. There's been measurements done on a tilted wind tunnel, actually in our lab, very many years ago, and they do what they are supposed to do. They do make sense if you just scale with gravity. And I, in the old days, used some low density materials, which is obviously the inertia then is wrong, but then you just normally do see that gravity behaves kind of okay. But no, if you want to do, that's Gerhard's thing. And I'm not taking this in a plane. I can promise you that.
There was actually a paper out just last week by Ralph Lawrence and I haven't read it, but the abstract seems to say that new measurements by Perseverance seems to confirm the parabolic flight experiments about much lower thresholds for dust lifting. So I don't know the value of the paper, but
okay. Yeah, no, I haven't read it either. Rolf, he writes so much, it's hard to keep up with him. Yeah, thanks.